All right. So welcome to this talk about how interaction between applications can hurt performance in your systems and what we can do to mitigate that and get better performance. So I'm going to start with this. You might be familiar with these types of surveys. This one was published by Datadog, where they asked Datadog customers how much CPU do containers that they provision actually use, right, out of the requests. And they showed that a lot of the containers we run at very low utilization, right? Like more than half of the containers run at a lot less than their half of their instances. And so, we're a big enough crowd here that I want to run a small survey. Can you please hand if you know what the average CPU utilization in a production cluster is? Usually like a small proportion. So only two, not a big sample size. So I'm going to skip. Do you want to just shout out what your average CPU utilization in a production cluster is? Or for right?
We're good. 20.
Right. So yeah, I started 20, and 20 to 40% is the results, are the results that I hear, mostly with, very few people say above 50. It's really hard to get that much. If you look at what the hyperscalers, like a lot of companies that have ton of engineering power to optimize their deployments, what they claim they do, it's between 20 and 40%. But what happened over the last 2 years is that some companies have been able to achieve a lot higher than the 20 to 40%. So Google was around 35% in 2011, and it rose to around 50% in 2019, which is kind of amazing. It's 1.5 times more in a big company like Google. So what happened, if you look in publications that they had, you can find two major causes. At least I was able to find those. One are advancements in vertical autoscaling. So that means choosing exactly the right CPU and memory requests for each pod so they can bin pack a lot more containers into the same number of servers. And, as a community, the Kubernetes community has access to these types of systems with horizontal, vertical autoscaling and things like Castanai and Perfect Scale, and there's a bunch of other companies. But you need another piece in order to make this actually work, which is mitigating the performance contention between container that result, right? Like you're packing all these applications in, now they're starting to fight for resources and their performance degrades. So you really need to handle this. And this is what we're talking about in this talk. And so, we said that some companies have had the ability to have much higher utilization. It's not a secret how they do it. There's been dozens of papers over the last 15 years explaining what noisy neighbors are and how to mitigate them. And I think there's enough out there these days that as a community, we can build solutions that are general purpose that we can use across the community to improve performance for our users and get higher utilization. And that's why I'm here. So I want to, in this talk, to cover what is the memory and cache noisy neighbor, and do I actually have it in my system? Then talk about, do I really need to solve it? Does it matter? Then talk about what are the potential solutions that we can build and what we're doing in the open source. So let's do it. I did my PhD in noisy neighbor mitigation, specifically network noisy neighbor mitigation. I then started a company that built eDPF-based network monitoring tools, which we sold to Splunk. And I'm a maintainer on the OpenTelemetry network collector, which we contributed. And I'm now working on noisy neighbor mitigation. Okay, so what is cache and memory noisy neighbor? So generally, what is noisy neighbor? We have applications that run on these physical servers. We like to think about them as running in the cloud, but actually there's physical hardware that they use. And they have to share the resources that are offered by the servers. When one application, right, like in the one in orange in this slide, uses a lot more than its fair share, then other applications cannot reach that resource, so their performance degrades. And that's noisy neighbor. And in this talk, I'm going to discuss these two resources, cache and memory bandwidth. Cache is the CPU, the memory that's on the CPU. So how does a cache noisy neighbor look like? Usually when you have your application, it fits into the different areas of the cache hierarchy like this. You might have in purple is your blazing hot working set, is the memory that your application uses the most. That fits into L1. And then you have the hot, warm, and cool working sets that fit into L2, L3, and DRAM. When you have a noisy neighbor running next to your application, the noisy neighbor reads memory very aggressively, so it evicts your application out of the shared caches, the L3 caches, and now your application has to access DRAM for its warm working set, which is slower. In the more extreme case of noisy neighbor, you have the noisy neighbor running in the logical CPU core, the hyperthread right next to your workload. And so it might evict your application from the other levels of the cache, L1 and L2. Sorry, I don't have a box there. So it evicts you from others, and then your application has to go to DRAM for basically all of its memory, right? In the most extreme case. So this can be a lot slower, right? Like L2 to DRAM is 50 times slower. So theoretically, your applications could slow down. Do they do it in practice? It turns out, yes. Google ran this experiment with their production workloads, where they ran some of their production systems with these noise generators with DRAM and cache. And what they found is for web search, which is the Google search node, there's 5 times degradation, slowdown when faced with a noisy neighbor. 5 times for ML cluster, which was one of their online machine learning text classification systems, and up to 14 times in memkeyval, which is a in-memory key value store like Memcache. So this actually converts production workloads. Now, these noise generators are very persistent. They look like big data analytics, right? Like they run very aggressively all the time, which is part of the reason why we don't run big data analytics next to our interactive workload, right? But does this happen with interactive workloads as well? It turns out the answer is yes. So in this experiment, MIT researchers ran a garbage collected workload next to Memcache. And you can see on the top graph, you have the memory bandwidth on the system. It's very low while running the experiment. But as the mark phase of the garbage collector starts, the garbage collected workload starts, the memory bandwidth spikes up a lot, right? Basically saturating. And if you look at the latency of Memcache, usually it's very low, around 50 microsecond P99.9, very reliably low. But then during the mark phase of the garbage collected workload, its latency spikes up. And this is like 3 orders of magnitude, 1,000 times slower for Memcache. So even a garbage collected workload can cause this type of noisy neighbor. And if you have applications that suddenly read and write a lot of memory, they could be noisy neighbors to other applications. So to see how this might work on a Kubernetes cluster, we wanted kind of a less of a synthetic experiment. It's still a benchmark, but we wanted to run a system with many components and see how they interact. We ran the OpenTelemetry demo, which we chose because it has around 20 microservices written in 13 different languages, which is the color scale. And it simulates an e-commerce application. You have, I think it's a telescope shop, right? Like, and this is what you see when you go to your observability vendors, right? The demo with this. And so we measured this metric, which is very common in papers, called CPI, which is the ratio of the cycle it takes a piece of code to execute divided by the number of instructions. And the idea is this. Your program is executing some number of instructions to service a user request. If there's a lot of memory contention, a lot of interference, then it's not going to be able to read from caches. It has to access DRAM. So it takes many cycles to execute that number of instructions. And if there's less contention, then it can access cache. It's a lot faster, then it doesn't take as many cycles. Here, cycles is like a measure of time. And so what we found on the OpenTelemetry demo is that most services experience around a 20 to 30% slowdown when there's high memory contention. So the top 5%, the 95th percentile memory contention versus the median, most applications are around 20 to 30% slower, with some applications suffering up to 3 times slowdown. So this actually happens in Kubernetes clusters. Okay, so should we actually do this? Should we try to solve this or not? Should we care? Well, think about it this way. We've been programmed. Here are 2 simulated systems, one with low load and another one with high load, right? And you can see this is the memory bandwidth, and you can see the spikes that you'd have from something like a garbage collector, right? And very intuitively, the high load system is going to have worse performance, right? Because you have these saturation events that cause a degradation, a slowdown in the other applications. So the more load you have on the system, the worse your 95th percentile, 99th percentile is going to be. And as operators, we've been programmed, we have it very ingrained. When we see bad performance, bad P95, P99, we immediately, what we do, we scale out the system, right? Like we run on more replicas. So we move from the high load to the low load system, right? That's what we do. So let me tell it another way. There's high load on the system. That causes this memory contention, which reduces the CPU efficiency because now applications can caches, which causes us to breach our SLOs. How do we fix it? We scale out. We reduce the load. And I think this is wrong. This is an anti-pattern. We shouldn't do it because it causes us to be inefficient, and it's not effective at mitigating all of the latency. It pushes us to a better place, but it doesn't really solve the problem. What we really want to do is to mitigate the contention between applications. And that would allow us to get higher CPU efficiency and higher load. And this is what the hyperscaler did. Basically, some of them to get better performance. So if they can do it, why can't everybody have this type of high utilization good performance? And just as another note, right? Like we have these 2 systems. When we go from the high load to the low load, right? Like we're pushing the latency, we're reducing the percentile latency lower, right? Like if we had high P95 percentile latency, we scaled out a little bit, the P95 decreased. But what about the P96, right? Like if we don't solve this, somebody is going to hurt, right? Like we can actually improve quality of life for our users if we solve this problem. Okay, so what can we do? Well, first thing, if we can only have observability and can only find the small number of pods that are really being noisy neighbor, there are some things we can do just by knowing what those pods are. First, we can adjust resources. It turns out if you try to squeeze down a garbage collected workload, squeeze down its memory footprint a lot, then its heap becomes very small, and now it has to do very frequent garbage collections. So just by increasing the memory that you allocate to that process, you decrease the frequency of garbage collection so you can become more efficient. Another thing you can do is you can go to developers and ask, your system is misbehaving, right? Like maybe it has a memory scan instead of using a hash table. Can you fix that, right? Like there are these patterns that cause high memory churn that are acceptable usually, but maybe not if it reaches the state where it hurts other components of the system, you can have this conversation. And, as a final resort, you can always isolate the misbehaving workloads to their own server so that they don't interfere with everybody else. So at least most of the services run well. And so even if you just have observability, there's a lot you can do to mitigate this type of noisy neighbor. But I'm excited about Automatic mitigation, where CPUs today have support to directly limit the amount of cache and memory bandwidth that each application can use. That's awesome, right? Like, so we can just, if you have a noisy neighbor, you can just tell the CPU, don't let it consume all of the cache, all the other Cs. And even if your CPU doesn't support it, like older CPUs and lower end CPUs, there's a lot you can do. For example, you can pin an offending workload to a core. You can tell it you only run on this core and you reduce the frequency of this core. So you slow it down. So you don't have to have, if you have a garbage collecting thread, it doesn't have to finish in 100 milliseconds if it's then going to be idle for 3 seconds, right? Like, let it take 3 seconds, but be very gentle on the system. I get this question a lot. Like, shouldn't containers take care of this for us, right? Containers contain. Well, it turns out they don't. We haven't built that yet. But there is a subsystem of the Linux kernel that supports this called resource control. And you can build on top of that, and that's, what we're aiming for. Right. So how would you build an automatic system to mitigate noisy neighbor? You monitor, find applications who are using more than their fair share, and then throttle them down. So you put them in a sandbox that can only use 20% of cache, let's call it, instead of 100% of it. And both Google and Alibaba Cloud have published papers that they have systems like that. So Google has been using a system using CPI, which I introduced earlier, since at least 2013 on their shared clusters. And Alibaba published in 2020 that they had been using this type of system for over 2 years on more than 1 million cores. Now, the problem is that applications change their memory pattern very quickly. So if you think about garbage collection typically takes between 1 millisecond and 100 milliseconds. Here you get these two graphs of the same system, one at of memory bandwidth utilization, one at 10 millisecond granularity on the top, and the bottom is the same data at 1 second granularity. And you can see that the top graph just has no signal. You just don't know who is the noisy neighbor. You just can't see it, right? Because things change too quickly. And so you really need to have very frequent measurements in order to discover noisy neighbor, which is very different from other methods of observability where you measure, you get these data points once every minute, right? Maybe 15 seconds. Here we're talking about 1 millisecond. So we set out to build something that would allow observability at 1 millisecond granularity. So let's talk about what we're building. So we want to measure every millisecond. You want to get this measurement on all of the cores, how much memory bandwidth each process running on that core is using every millisecond. So you want to sample. The problem is you want to have very tight measurements, but what actually you're getting is some jitter, right? Like how, you have these measurements. How do you make them really precise, right? Like you're fighting against this jitter in measurement. Because if you're trying to get 1 millisecond interval and some of them are shifted 1 millisecond here and 1 millisecond there, and another is just 2 milliseconds long, like how does that data make sense? How can you read that? And so we built using eBPF and high resolution and the kernel's high resolution timers. We built these synchronized timers where they tick every millisecond on every core. And we measured the difference between the fastest core to tick and the slowest core to tick. And you can get pretty good. This is like an Amazon machine with 96 cores. You can get it pretty tight, like most of the measurements under 10 microseconds jitter. So this is actually plausible. You can actually build a system with this. And so we did. And so this is how that OpenTelemetry demo looks like. The cache misses in 1 millisecond granularity. So this is half a second of the run. And the colors here are the different processes running on the system. And here you can see an anomaly, right? So the OpenTelemetry collector, there's a 30 milliseconds there where it has a lot of cache misses, more than the ordinary. Now, if I move that graph to the top here, And on the bottom, I'll plot the cache references. So this is the memory that doesn't hit, that is able to hit cache. You can see that there's a decrease around the same time, right? So that amount of memory misses looks like it evicted other applications from the cache, and they were not able to hit the cache. And so the overall throughput from the memory hierarchy decreased. This is like the slowdown, right? You can actually see it here. Right now, we're in the phase where we're getting these 1 millisecond measurements, and we're building these detection mechanisms that using these 1 millisecond measurements can tell you, okay, now this application is being noisy neighbor. Now that application is being noisy neighbor. And what you could do with it is you can get this type of observability of here, this application is being noisy neighbor 2.2% of the time, 0.1% of the time. So you can see which of your applications are hurting performance for others. And I'm really excited towards the possibility, getting there where you can do automatic mitigation. Now that you have these signals, this is being a noisy neighbor or that, to move it into a system, like I mentioned earlier, where you can actually go and throttle the offending application. We put a lot of effort into making the collector itself be low overhead, right? Like you're collecting measurements at 1 millisecond granularity that it could take a lot of CPU and memory to get these buffers and flush them out. So memory utilization, we benchmarked under 350 megabytes, even on a system with 96 cores. And the CPU utilization increases with the amount of workload. The more applications use memory, the more they context switch. So you have to account for which application is using how much memory bandwidth. So there's an increase. The more in the red on the bottom is how much utilization the application had, and it reaches 30 cores, 30,000 millicore. And in blue on the top is how much the collector took, which rises towards like 200 millicores. So that's 0.75% CPU overhead. So bottom line, 0.75 percent CPU overhead. But I want to make the point that even if that CPU overhead was 5 times larger, right? Like if it was 5%, so then it would still be okay as long as it would help you mitigate noisy neighbor. So let me give you an example, right? Let's say you have a system with 40 milliseconds median, average utilization, whatever you want to measure, and then P95 of 250 milliseconds. If I could decrease your P95 from 250 milliseconds to 75 milliseconds by reducing noisy neighbor, and you'd have to pay 5% in the average, so increase the average from 40 to 42 milliseconds, I think many operators, many people would just say, like, yes, let's do this. This is completely worth it. Right? Like predictability matters. And so I think like 5% is way overdoing it. Like the overhead is not going to be 5%. We're already reached like 0.75%. But even if it was higher, you'd still want to do it. If you want to deploy it, the Helm chart's available. There's documentation. There are scripts to plot the results, and I'm happy to help you out. I'm actually looking for kind of early users who might want to see how their system behave, and I'll work with you to make sure that your side project is successful, or your project. Okay, so my contact details are on the repo. This is the repo. It's open source under an Apache 2 license, so welcome to use it and contribute to it. And I'd really love to invite you to contribute. The project itself is written in Rust and eDPF. If you want to try to dabble in that, but we're also looking for contributions in these benchmarks and stress tests, and some data analysis too, from the 1 millisecond granularity data, extract noisy neighbors. And if you want to run the collector, we'd love to help you so that we know that it works for a large community of people that, to iron out all the kinks. And hopefully this will help everybody get to the higher utilization, save some money, and also improve performance for users so that we're not in this, like, this is fine, everything's burning, everything's noisy around us. So with that, thank you, and I'll be available outside for questions.